Hello, I am CThomas, and today I will be talking about electron configurations. Electron configurations are commonly used to describe the ground state of an atom. In addition, they can be used to show the difference in orbitals between charged atoms, such as anions and cations, and atoms in the ground state. One practical use to note is that electron configuration is used in PES, or photoelectron spectroscopy, to identify the numerous spikes on a spectroscope graph. In order to be able to write electron configurations, one must first understand the orbitals on the periodic table. The s orbital is always written first, followed by the block immediately to its right. Say I were writing the electron configuration for carbon. I'll start by moving to the s block and writing 1s2, as we start with the first row of the s block and the first two elements given. Since there's nothing else in this row, we move to the second row, writing 2s2. Now looking to the right, we actually see the p block. We count through this row until we reach carbon. So in this case, I would simply put 2p2. And now I've completed the electron configuration for carbon. Now when we look at the periodic table, we see a long chart full of elements. Writing the configurations of elements nearing the bottom will take an irrational amount of time. So we use this shorthand technique called noble gas notation, where we abbreviate the configuration by taking the noble gas one row above the atom, then starting a configuration from there. Let's take iodine, for example. If we refer to our periodic table, we see that krypton is the noble gas above iodine. So we would write the atomic symbol for krypton in brackets, then continue the configuration from there. So this would translate to being a bracketed krypton followed by 5s2, 4010, 5p5. Now these rules do not translate the same for every atom. Both copper and chromium, as well as others, are irregular. Their furthest valence shell is filled differently from the rest. This is due to the orbital wanting to be filled until balanced. In regards to chromium, you might think the configuration would be bracketed argon followed by 3d4, 4s2. However, if we look at each orbital in the boxes and arrows diagram shown below, we see that the 3d orbital would only be 40% full, as there is an arrow missing to complete it, while the 4s orbital, on the other hand, is fully complete, amounting to 100% completion. So we would rearrange the distribution so that both the 3d and 4s orbital would be equal to 50% each. This same logic applies to copper's configuration, with having to rearrange the distribution in each orbital so that they are balanced. This has been electron configurations, and I hope that was helpful.